We're going to talk about most of the things that I could ask you to do with a redox process with this relatively simple looking balanced equation here. First, this isn't a great balanced equation as it's written, as there aren't states of matter included. So I'm going to do that first. You'll be expected to do most of these as well. Look to the periodic table if you don't know the state of matter of the elements, as the color-coded version of it will list the different states with different font colors. There's no indication here that this reaction was run in solution, so the product's going to be a solid. And I wouldn't expect you to know this come quiz time though. So I would either have to do solution chemistry so that you can apply the solubility rules from section 2.2, or I'd have to give you the states of matter as I just did there. You can pick one of two things for your next job. You can either go ahead and divide this into half reactions by placing the same elements on the reactant and product side of the same half reaction and then assign your oxidation states. Or you can assign your oxidation states to the full reaction and then divide your process up in a bit. I like to do the latter, so consider our oxidation states assigned. There are two elements on the reactant side, and all elements are going to have an oxidation state of 0, even diatomic and polyatomic elements like our chlorine here. For the product, you have a transition metal, so we should make sure that we can assign the oxidation state on the anion first and then use that to find the oxidation state of the transition metal. The anion is chloride, which will adopt a charge or an oxidation state of 1-, but there are 3 of them, giving a total of 3-. The iron, therefore, will have to have a charge or an oxidation state of 3+ to cancel out all of those minuses. Remember that I can use oxidation state and charge interchangeably here because I have an ionic compound. Note also that you wouldn't write the 1 in for the chloride. I just did this to make sure that the tiny minus sign didn't get lost. This isn't an official notation anyway. We're just writing info that might make our life easier, so my choice is fine here. On to writing our half reactions. You're going to divide this reaction up so that like elements go in the same half reaction. Lead isn't going to turn into chlorine no matter how hard you try, so you don't need a reaction that claims that even could happen. What we do need is a reaction that says iron metal might turn into the iron 3 cation, and then another separate reaction that says chlorine gas might turn into the chloride anion. We'll come back to the chloride reaction in a bit. I'm going to get rid of it to clean up our slide. Notice that I've brought down the stoichiometry of my overall reaction when I wrote this half reaction. Yeah, both of these half reactions could have been reduced, but if I leave them as they are right now, I'll probably have a better shot at getting the number of electrons transferred correct when I get towards the end of this. So trust me for a minute and we'll carry on and we'll fix it if we have to later. Now let's finish up this iron half reaction. I say finished even though the atoms are balanced because the charge is not. I have 2 moles of iron metal on the reactant side and both of moles are neutral. So the sum of the charge for the reactant side is 0. On the product side, I have 2 iron cations and they each have a 3+ charge. And this gives me a total of 6 pluses on the product side. This is no bueno as these are obviously different numbers and my equation is not balanced until these are the same. So I have work to do to make sure these values are the same, and the only way I can do that is by adding electrons, which are negatively charged. Electrons are literally the only thing you can add. Don't try to do other things. Since those electrons are negatively charged, they're going to need to be placed on the side that is more positive to begin with, and in this case, that's going to be the product side or the iron 3 side. Now, how many electrons should you add? As many as you need to cancel out the extra positive charges that are present. The product side for this half reaction is more positive than the reactant side by a value of 6. So I added 6 electrons to make both sides have the same numerical value for the charge. Note that even though I made it to 0 on both sides of the reaction in this case, that's not always going to be my goal. I don't need the charge to be 0, I need it to be equal, whatever that value happens to be. And when I say add, I mean add them to the reaction themselves. Notice that I got rid of the charge on the iron solid since I'm trying to work towards a valid balanced equation. The charge on the cation needs to remain to differentiate it from that solid. At this point, I have a lovely, mostly balanced half reaction. Again, I say mostly balanced because it really could be reduced. I just haven't gotten to the point where I want to do that yet. It's at this point that I can determine whether I have a reduction or an oxidation process. Electrons that show up on the product side, as they do here, are considered lost. Losing electrons is an oxidation process. So iron, forming the iron 3 cation, is going to be an oxidation process. We could also say that iron solid is oxidized. The oxidation of iron can only occur if something else is reduced at the same time. So in addition to listing iron solid as being oxidized, we can also state that it happens to be the reducing agent. This is the species that forces the other half reaction to occur. Back to our chlorine half reaction. There are 3 neutral chlorine molecules on our reactant side of the equation. So again, the reactant side of my equation is neutral, 0 charge overall. There's 6 individual chloride ions on the product side, 3 from each salt, but you have 2 formula units of that salt, 6 total. This gives us a charge of 6 minus on the product side of the equation. Again, electrons, which are negatively charged, are the only thing that I can add to balance the charge here, and those are going to need to go on the more positive side. That's the reactant side in this case, because even though 0 isn't positive, it's more positive than 6 minus. Notice that I dropped the oxidation state on the molecule entirely, and I dropped the 1 on the anion so that I can follow the standard notation for my reactions. When electrons appear on the reactant side of the equation, they are considered gained. The chlorine has to gain them before it becomes the chloride ion. Gaining electrons is a reduction process. The chlorine molecule is reduced. The reduction process cannot occur without forcing the iron oxidation that we've already seen. So we can also say that chlorine is the oxidizing agent. One last thing to discuss, and that's the number of electrons that we can transfer. Notice that the number of electrons lost in the iron half reaction equals the number of electrons gained in the chlorine half reaction. You're not done working with the redox process until this is the case. Because I brought down the stoichiometry of the original balanced equations into my half reactions, I ended up with the correct numbers here. This is why I did that. Keep in mind that there are a total of 6 electrons transferred. The same 6 that are lost in my 1 half reaction are gained in the next. You need these values to be equal, and you will not add the electrons together. There aren't 12 transferred. We're just describing the same 6 electrons in 2 different ways. One very last step. To best report the half reactions, we would want to reduce the coefficients at this point. Had you not kept the stoichiometry of the original reaction throughout the entire process, you would need to find the least common multiple between the 2 electron values right now to find the total number of electrons transferred. You'll get 6, just like we did, whichever way you do it.